tube here, you will get something that is called nanotube. Why these things are so interesting? They may have properties that are very, very attractive and no other materials have. People claim them to be the strongest fibers known. They may have electrical properties ranging from semiconductors that can be used in electronics to metal, so they can be used as nanowires. And they are extremely small, and they come in all sizes and all shapes, so you can build a lot of things of these small tubes. Particularly, one of the speculation in the beginning of the nanotechnology era was to use nanotubes as tiny pipe to deliver drug to single cells or probe single cells. And we are working on development devices that can do this. But it appears that scientists didn't even know how liquid and whether a liquid can flow through such a small tube. So what students in my group do, they study how liquid behave when it's confined in this tube. For example, when you have a water in a capillary that is 1,000,000 times smaller than a standard tube here, will it flow with the same speed?
Does it?
Or no, it doesn't.
Okay.
It appears to be much, much slower.
Yeah.
You can observe single molecules, how they move there.
Mm-hmm.
And we are trying to understand how to modify properties of these tubes that we can provide fast transport. Or maybe we can take advantage of this very, very slow flow rates that we can, in a very controlled manner, deliver single molecule of drug, for example, to a cell without overdosing ever.
So there's a tremendous potential for control there.
Absolutely. Here. They provide tremendous potential of control, that we can make patches that can deliver drugs through skin, for example, here, or we can probe a single cell or do eventually operations on single cells using nanotube syringes for much of this work.
That's
that we can
very exciting.
do really work that is currently impossible at all.
Would this affect cancer cells as well?
This is one of probably the most important applications. People have been trying to use already now various nanocapsules to attack cancer cells. For example, in England, a technology was developed to deliver very small glass spheres to cells, and then by heating them, using microwave heating, like a microwave oven. Only these spheres were heated, so only cancer cells were attacked without damaging other tissue. In a similar way, we can deliver radioactive isotopes selectively to cancer cells. For example, when they are encaged in fullerene molecule cage. This is a molecule consisting of 60 carbon atoms and having a shape of a soccer ball. If you have a radioactive isotope atom inside, it will always stay in this cage in the body because there is no force in our body that can break carbon-carbon bonding. So it can be then safely, hopefully, removed later from the body without, again, staying for a long time and damaging healthy tissue.
These are still applications that are in the theoretical stage, I take it.
Some of them, for example, this glass sphere technology is already approved and used, at least in Europe.
That's very
Some
exciting.
other technology for drug delivery are still at the stage of either investigation or awaiting FDA approval.
Okay.
Technology that we are trying to develop with nanotubes and nanosyringes is definitely probably 5 to 10 years from real applications here. There is a long way to go, but it may allow new levels of gene engineering done, new levels of cell technology, and in general have a tremendous effect on nanotechnology and our ability to treat diseases that seem to be incurable today, like cancer or HIV.
As I hear you speak, I realize how cross-disciplinary this field must be, and I know that you have a number of joint appointments, I think, in different colleges, departments of engineering, but I could see this crossing to the sciences, into physics and chemistry, and of course in the medical school. Is this institute that we have here at Drexel, is this a very cross-disciplinary sort of operation? Who's involved?
Yes, it is. We have currently more than 30 scientists who have registered with AJ Drexel Nanotechnology Institute, and we are still building this institute. The physical building for the institute will be ready probably in less than a year, but currently we're trying to coordinate efforts of scientists working on this campus and also in the medical school. Since Drexel acquired the medical school a year ago, MCP Hanneman University became Drexel College of Medicine. We have acquired a great potential of medical scientists and doctors who are interested in bio-nanotechnology. And definitely not only physicists, chemists, and engineers should work together. We really need biologists, cell biologists, immunologists, biochemists, and medical doctors to address all these problems here. So it's a very interdisciplinary field.
I would think the coordination of people in these various fields would be quite a challenge. Is that your role?
It definitely is. This is what I'm trying to do. I'm learning myself continuously about biological aspects and medical aspects of nanotechnology. So I cannot stop learning, and I always feel that I lack specific knowledge in many, many disciplines. And despite the fact that I have degrees in different areas, and I hold joint appointments therefore in chemistry, materials, and mechanical engineering, I still need to know a lot. And very often, the only thing I know about certain medical applications, that there are these people at Drexel College of Medicine who are expert in the area. And often for me what is important is to be able to find the right people, to enable them to form a team and work together. And this is what is the goal of AJ Drexel Nanotechnology Institute. We want to coordinate these activities, help scientists from different fields, different disciplines, work in different colleges and departments, come together and work as a team on projects that would be impossible without efforts from people from different disciplines. And we're also trying to teach students in a similar way. So one of the goals for our institute is to develop programs that will help students to acquire knowledge in the nano field and beyond the borders of their small disciplinary area. Here, that people who work in mechanical engineering can also learn some biology and bio-nanotechnology, for example, here. In materials engineer, learn more about surface chemistry and colloid chemistry, other things that they need to understand if they want to develop materials at the nanoscale.
Well, it sounds to me like it lends itself to the model of the Postmodern University, which is the university without walls, without departments, where people can pick each other's brains freely.
Well, I think this is what will come to. And it was also interesting, in the new building that is under construction now, we're planning to build joint use labs. Therefore, not individual faculty lab, not Professor DiNardo's lab or Professor Gogotsi's lab or Professor Palmizzi's lab. We're planning labs dedicated to certain topics, electronic nano devices or nanoporous materials, where people from different departments, different colleges can come and work together, solving a certain problem. And they will have instruments, equipment they need for their research. And we already have a lot of joint activities like this at the university, and I hope that this type of activities will expand and grow.
It's sort of a revolutionary way of looking at the university and research, I think.
Well, I believe just education need to follow changes in technology and society. So if technology changes, we need also to redefine disciplines. Mechanical engineering, for example, today is very different from mechanical engineering 100 years ago.
Absolutely.
People don't necessarily work on gears or solid mechanics anymore. People in mechanical engineering department at Drexel, for example, work on biofluids, on flow of blood in vessels. They study development of produce new sensors. They combine electronics and mechanical devices. They do a lot of things like working on plasma treatment at the atomic and molecular scale here. So things that would not fit mechanical engineering field before. And very often, when we hire people here in the College of Engineering area of nanotechnology, this person would naturally fit at least 2 or 3 different departments and would be able to work in any of these departments. So it means that we really will have to redefine, I think, in pretty near future, what these disciplines are, because technology goes in a direction where you need to know all or be able to combine biology and mechanics and electronics and chemistry together to develop useful products.
That is really very exciting. And I guess I have to add, as a humanities person, someone from the other side of the university, that when you speak about particles so small that you can't see them, that the notion of the imagination and the ability to describe, I guess, for the layperson, maybe that's where our role comes into play, to help translate what you scientists understand so well, but what the rest of us perhaps, I mean, it's imaginary.
Yeah.
That's exciting.
Well, that's true, and I believe there is much larger contributions that humanities and scientists working in humanities can do. There are many ethical issues in nanotechnology. It's wonderful when you can have sensors distributed and sensing everything from temperature of air outside to level of illumination in your clothes, for example. And you have a smart clothes that will illuminate at the moment, for example, when there is an approaching car, a noise of approaching car, as the night heard here. But on the other hand, if you have the sensors everywhere, they can send also information everywhere here. How much do you want other people to know? Do you want other people know what is your blood temperature at that moment, whether you have fever or not, or a lot of other things here? So there are many ethical issues that need to be raised at the same time with the development of the technology.
Those are important questions, yes. Thank you very much, Yury Gogotsi. You've really, you sort of opened up this field, which was, I think, is mysterious to a lot of us, lay people. And it's been very helpful talking to you. And I want to thank you for joining us at the Drexel interview, and we hope to have you join us again next time.